So, first thing you're going to have to learn is some logic basics. This slideshow, or whatever, is going to talk about propositions and connectives. You got to know logic and the basis of logics. This is the bread and butter of mathematics. We have to prove things that are true. Anyway, blah, blah, blah. So, first off, a proposition is a statement that is either true or false. For example, Megan was born in 1855. This is obviously false, but it has a truth value, true or false. Something like Rome wasn't built in a day. This is true. It has a truth value, it's true or false. Something like x is greater than 4. This is not a proposition. Sometimes it might be true, sometimes it's not true. We don't know what x is. Similarly, if you had a statement like, she has red hair. That's not true or false because you don't know what she is or who she is. She is the same thing as the x. Another weird thing are paradoxes. To say something like, this sentence is false. Well, if it was true, that means the statement is false, but then it's false. So this is weird. If the statement is false, which means the sentence is true, which says the sentence is false, you just keep going back and forth. This sentence here, the sentence is false. It's neither true nor false. It is what we call a paradox. So this is not a proposition. So now let's look at connectives. The first connective we'll look at is a conjunction. Given two propositions, P and Q, a conjunction is read P and Q. It uses this little caret symbol. This is going to be true when they are both true. Hence the and, P and Q. The LaTeX for this, I stuck it up here in the corner for you. P/wedge Q gives you this notation. If I don't say it, I'm usually going to just stick some of the LaTeX code that you might need up here, since I'm making you type your homework up. The next conjunction I want to look at, and so let's look at the truth table for this. So since we've got two things, there's two possibilities for the P and two possibilities for the Q. You've got true, true, false, false, true, false. So this is all four possibilities of truths and falseness with the P and the Q. So the statement P and Q is only true when both P and Q are true. Every other time it's false. The next combination we're looking at is called a disjunction. It's read as P or Q, and you have this little V thing. Think of it as union. If you do set theory, union usually is the set of things that's in this set or in that set. The one thing that's funky about or here is it's not like English. Because typically I'll say, oh, do you want ham or do you want bacon? You don't usually say yes. If you want both, that's usually not one of your options. But with here it is. What I mean by that is this proposition is still true even if they are both true. So the truth table for this one, P or Q is, this is a typo I forgot to fix. Okay, so this should be a big old hunkin' F right there. So pretend that's an F there. The only time an or statement is false is when the P is false, the Q is false. So, the last thing we can do to propositions is a negation. Tilde P means the opposite of P, like negative P. So when P is true, not P is false, etc. There are many different notations for this. You can say, and the LaTeX for it is, if you say /tilde P, this puts this little wimpy looking tilde over the top of it. I don't tend to use that one. I'll use it in PowerPoint because it's really easy to type it up, but in LaTeX, no, I don't do that. Another possibility is /neg P. I kind of like that little square thing. It looks funky. But that's another form of saying negation. See, neg. And if you want something that looks more like what I have in PowerPoint, you can say /sim, as in similar. That gives you the little tilde P. I will use both, and I'll be a pain in your ass, because you will go, what does she mean? Why does she keep switching? Well, because I'm a ditz, and I switch back and forth, depending on what program I'm in or what I think to type at that moment. So when you have to negate something, you want a useful negation. And what do I mean by that? Well, one example I used to use is the proposition that Pat is a girl. The negation of that would be Pat is a boy. Well, of course, that's not true anymore. I mean, she could be, is she cis male? Is she cis female? Is she trans? So that's not a very good example anymore. But the idea is, if you can get a, if you don't have to, don't just throw a not in there for your negation. Sometimes that's your only choice, right? You are a girl, you are not a girl. But sometimes if you have an opposite, something else, you want to put that in there. Like this one. 10 is less than x, or x is greater than 10. For this to be false, you want to get both possibilities. You're going to say 10 is greater than or equal to x. Either one of those cases would be a negation for 10 is less than x. X is a composite number. Well, to be composite, the definition is not prime. So the contradiction to that, the negation for that would be x is prime. Now this next sentence, you want to think about what would make this statement false. This says, I am sick and I am tired. For this to be false, that means one of those two statements has to be false. They don't both have to be false. You don't want to say, it is not true that I am sick and tired, because that's the same thing as just throwing a not in there. So to change this, the negation for this would be, I am not sick. Sorry, I don't know the opposite of sick. I am not sick, or I am not tired. The negation of an and is an or. And similarly, the negation of an or is going to be an and. We'll formalize that on another slide, but right now, you want to take this and that negated becomes not this or not that. I like yogurt, but I don't like ice cream. But in here acts like an and. When you are using this in English, you are saying that both of these things are true. The but's just more of a, yeah, but this is kind of different. But it's still basically as a conjunction, it works as an and. So the negation of this, of I like yogurt and I don't like ice cream, would be I don't like yogurt, or I don't like yogurt, or I like ice cream. Here's a more mathy one. The negation of x is less than y would be x is greater than or equal to. And the negation of m squared is less than 1 would be m squared is greater than or equal to 1. And since we're negating an or, we need to change it to an and. So the negation, x is greater than or equal to y, and m squared is greater than or equal to 1. So, I do want you to be able to do a truth table. To do the LaTeX for it, you should be able to cut and paste from this slide if you need to, but let's go through the syntax for a table. You say begin tabular, and actually it also works for array. I just recently discovered that, and it's actually kind of nice. But anyway, we'll do this one because it's what I hear. This is what's here. Slash begin tabular, meaning I'm going to do a table. I have C, 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 C. This means I have 1, 2, 3, 4. I'm going to have 5 columns. The C doesn't stand for column. The C stands for centered. Everything in the columns will be centered. These vertical lines say, okay, I want you to give me vertical lines throughout the whole table. H line means horizontal line. So I'm going to start the table. I'm going to draw a horizontal line. The first line of my table will be a P, ampersand between what's in the columns. So I've got a P in the first column, a Q in the second one. The third one is the negation of P. Notice here I have dollar signs. The slash neg is a mathematical command, so I have to have dollar signs around this statement. P and Q are just P's and Q's. I didn't need to put dollar signs. I could, but I didn't need that. If you use, instead of tabular, you use the word array, then you would need a dollar sign before it, but no dollar signs on the inside. So that's kind of nice. Okay, let's keep going. The next column is P wedge Q, and then the next one is PVQ. H line, H line. So that means I'm going to have 2 horizontal lines after this header. You'll see what it looks like in a second. Now, everything under here is going to be true, false, true, true, false, false, true, true, false. So first the P column is going to need to be true, 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 false, false. Q will be true, false, true, false. I negate it. I wedge it. Let's just do the line. So true, true, false, true, false. In this first column row, I actually made an effort to line up the ampersands, but then I said, screw this. This is pain in the ass. Don't need to do that. He can figure it out. So the rest are all scooched together. So we've got true, true, false, false, true. I'm not going to read that. That's boring. There's your table. The two lines actually made it look like two boxes, which was kind of nice. Here my P or Q is correct because I've got the false in the last one. Everything is centered. I did capital F's and T's, so I've got capital F's and T's here. Everything works out nice. Definition. Two propositions are equivalent if and only if they have the same truth values. And a denial of P is any proposition that is equivalent to not P. So what does this mean? We'll have a couple of theorems, and the only way we can really prove them is by doing a truth table for them. Things that are always true. A tautology is a proposition that is always true, and a contradiction is a proposition that is always false. One statement we use to kind of show you what a tautology is would be P or not P. This is always true. If P is true, then the statement is true. If P is false, then not P is true, so the statement is true. Tautology, so this is kind of the shortest, simplest example of a tautology. Contradiction is something that is always false. On the same take, we're going to say P and not P. One of these is true, one of these is false, so it's never, the statement itself, P and not P, is never true. So it is a contradiction. So if I know something is a tautology or a contradiction, I can go ahead and replace the tautology with a T and the contradiction with an F, just to make our quote-unquote calculations easier. Now, the neat thing about T's and F's with ands and ors is they act like identities. What do I mean by that? If P is just average Joe statement, a T and a P, true and P is the same thing as P. So this acts as an identity, like 1 times 5 is 5. 1 is the identity. In terms of or, F or P gives you P. So F works as the identity under or. And just like 0 is the additive identity, but then in multiplication it makes things go away. You always get the 0 back when you multiply by 0. If I take a T and or it with something, I'll always get the T back. So this is kind of like a 0. And F is kind of like a 0 in the and, because F and P will always be false. So if you can simplify your expressions, it's sometimes good to do that. Again, here's the law tech in the corner. This is the kind of the beginnings of Boolean algebra. We're not going to get really heavy duty into it, but it's a cool class if you want to do it on its own. First, I want to talk about a couple theorems in Boolean algebra that we'll use a lot. This is the one we talked about with the ands and the ors and the nots. If I negate P and Q, that is equivalent to not P or not Q. Similarly, if I negate a P or Q, that's the same as not P and not Q. These are known as De Morgan's laws. And, I can't see my... There. Hopefully that brought it back in the screen. And the only way you can prove these right now is doing a truth table. And so I typed up the truth table for you for the first one. Over here, you have the truth table for not P and Q. So you get false, true, true, true. And then over here, I have a P column, a Q column, not P, not Q. And then I put them together. And notice I get the same thing here that I got over here. So because the truth tables are the same, these two statements, this first statement here, they're equivalent. The second one, I'll leave for you to do for homework. The next theorem I want to look at is the distributive law. And distributes over or. See, I've got P and Q or P and R. So the and distributes and the or distributes. Now, I didn't want to do a truth table for this. Oops. I didn't want you to see it before I did it. But it's a good example of thing. We have 3 propositions here, P, Q, and R. So I'm going to need more rows because there's 2 possibilities for P, true or false. 2 possibilities for Q, true or false, and 2 possibilities for R, true or false. 2 to the third is 8, so I need 8 rows to get all possibilities. When you are doing these, you want to be very OCD, very anal retentive, to make sure you get every possibility. What I do is the last column will alternate 1, 2, 1, or true, false, true, false, true, false. The Q is going to be true, true, false, 2 at a time, and then the P will be 4 at a time. And if I had another variable, then I would have 8 at a time to make it bigger. So here is the left side of my equivalence. I have P, Q, R. This is where I ORed the Q and the R. And this is where I took the P and I AND it to this column. So I'm looking at, this is a true, this is a true, the whole thing is true. True, true, I got a true. And we don't need to go through all this. So this is the left side and this is the right side. Oh, I didn't do the little red squares. Oh, sorry. So we can see that this column is the same as this column. So therefore, they are equivalent. I want to do a couple of examples, but this is getting kind of long. Maybe I shouldn't do it. So I'm going to pause this, stop this here, and I will do the examples on the next video. But that's basically the stuff we want to cover for now. The next video will be examples, and then I will do implications.